Today we are going to study about potential due to a dipole. We know that a dipole is a system of two equal and opposite charges separated by a vector distance. So from figure we can see that we have a negative charge here and a positive charge here which are separated by a distance 2a. So the center is a distance away from the negative charge and positive charge, and we need to find the potential at P due to this dipole. We need to find the potential at a point P due to this dipole, and the point P is at a distance r from the center and at a distance r1 from the positive charge and r2 from the negative charge. We can draw the figure like this and let this angle be theta, and we draw perpendiculars from this positive charge to this point or this line R to the point C, and from negative charge we draw perpendicular to the point D. So what we will do is that to find potential at P, we will find potential at P due to this negative charge alone and due to this positive charge alone, and then we will sum it up. So first, potential at P due to positive charge, that is V1 is equal to KQ by R1, and potential at P due to negative charge is V2 is equal to minus KQ by R2. The negative sign shows that this potential is due to this negative charge. So total potential at point P is equal to V1 plus V2, that is equal to KQ by R1 minus KQ by R2. So we can take KQ outside, KQ into 1 by R1 minus 1 by R2. Now we need to find this R1 and R2. So from figure we can say that R1 is equal to, from figure we can say that R1 is equal to this distance, that is R minus this small distance, that is R1 is equal to this entire distance R minus this small distance OC. So from figure R1 is equal to PO minus OC, that is PO minus OC, and PO is R and R minus OC. R1 is equal to R minus OC, and from the triangle OBC we can find cos theta equal to, from this triangle we can find cos theta is OC divided by A. Cos theta equal to OC by A, and from this OC is equal to A cos theta. Therefore we can write R1 is equal to R minus A cos theta. Now we got R1, now we want R2. From figure, R2 is equal to PD. R2 is the distance PD, that is PO plus OD, that is PO plus OD. PO is R, and we can write R2 is equal to R plus OD, and from triangle OAD, that is from this triangle we can find cos theta as OD by A. From that triangle, we can find cos theta, which is equal to OD by A, and OD is equal to A cos theta. So we can write R2 equal to R plus A cos theta. Now we got R1 and R2. We can substitute this to the equation of potential, that is V is equal to KQ divided by 1 by R1 minus 1 by R2. Substitute the value of R1 and R2 here. 1 by R minus A cos theta plus minus 1 by R plus A cos theta. So this will be KQ divided by KQ into 2A cos theta divided by R square minus A square cos square theta. So from this, Q into 2A is P, that is dipole moment. P is equal to strength of one of the charges and the distance between the two charges. So we can replace Q into 2A as P, that is equal to K into P cos theta divided by R square minus A square cos square theta. Now assume that R is very greater than A. That is, we are finding the potential at a point which is at a very large distance, So if R is very greater than A, we can write R square minus A square cos square theta approximately equal to R square. So the final equation for potential due to dipole is Kp cos theta divided by R square, that is equal to 1 by 4 pi epsilon 0 P cos theta divided by R square. So this is the expression for potential due to dipole at a distance r away from the center. This is the expression for potential due to dipole at a distance r away from the center, and theta is this particular angle. Theta is this particular angle. From this, it is clear that the potential due to dipole is inversely proportional to r square. We have seen that electric field due to dipole is inversely proportional to r cube, but potential is inversely proportional to r square. Okay, now we have two cases. Case 1 is potential along axial line. Potential along axial line. That is, we are going to find the potential at a point along this axial line. At a point here, we are going to find potential along axial line. So the theta will be 0 here. Theta is equal to 0. Cos theta equal to 1. So potential, we have the expression 1 by 4 pi epsilon 0 P cos theta divided by r square, and theta is equal to 0 here, so V is equal to 1 by 4 pi epsilon 0 P by r square. So this is the expression for potential due to dipole along axial line. We can see that it is also inversely proportional to r square. Now next case 2, which is the potential along equatorial line. Potential along equatorial line. That is, we are going to find the potential due to dipole along this equatorial line, that is perpendicular to the dipole, or the exact normal to the center. So here theta is equal to 90 degree, theta is equal to 90 degree, cos theta is equal to 0. We have potential V is equal to 1 by 4 pi epsilon 0 P cos theta divided by r square. Here cos theta is equal to 0. Cos theta is equal to 0. Therefore, potential is equal to 0. So we can say that potential due to dipole along equatorial line is 0.